Let's review all the topics on analytic geometry. We're going to talk about the vectors, operations with the vectors, and also we're going to talk about the equation of the lines and the planes in higher dimensions using the vectors. So usually the vectors are defined with the 2 points. They are called the starting point of the vector and the ending point of the vector. But there are special vectors which always start from the origin. So this kind of vectors are called the position vectors. So the position vector is a vector which starts from the origin. Basically, we can define a vector using 1 point, for example, 2, 3, and 4. What does it mean? It means that the vector starts from the origin and its ending point is at the 2, 3, and 4. So now, if we're given a vector using the 2 points with a P0 and P1 point, I can move this vector to origin in order to make the position vectors. And this is legal to do unless we're not going to change its direction and the magnitude. So the way how we need to do is we just need to subtract the starting point from the ending point, and this is going to be a position vector. So let's say we're given a vector we're given some point P0 with the coordinates 2, 3, and 4. And the point P1, which is the ending point of our vector, is given with the coordinates 1, 1, and 2. And the position vector, which corresponds to this starting point and ending point, is going to be obtained by subtracting the P0 from P1. So this is going to be 1, 1, 2, minus 2, 3, 4. So this is going to be equal to the minus 2. So I'm going to subtract these 2 points basically by component by component, right? So the first component from the first component is going to be minus 1. So the second one from the second, it's going to be minus 2. The third from the minus the third one, it's going to be minus 2. So let's talk about the operations over the vectors. So if we are given a vector in general case, right, with some components u1, u2, u3, and the second vector with the components v1, v2, v3, where all of them are the numbers, we can add the 2 vectors, and when we add them, we need to add them component wise as we did before, right? This is going to be u1 plus v1, u2 plus v2, u3 plus v3. This is going to be again a vector with the same dimensionality. So another important operation on a vector is called the dot product. So when we multiply the 2 vectors with the components u1, u2, u3, and to the second vector with the components v1, v2, v3, this is going to be, as a dot product, this is going to be a constant which is obtained by multiplying the first component of the first vector to the first component of the second vector plus the multiplication of the second components plus the multiplication of the third components. So this is going to be a constant. So we can find the lengths of the vectors if a vector is given with the components u1, u2, u3. Its length is going to be equal to the u1 in the square plus u2 in the square plus u3 in the square, and then we need to take the square root of this. For example, if the vector is given with the components 2, 3, and 4, its length, or sometimes we call this as a norm of the vector, it's going to be 2 in the square plus 3 in the square plus 4 in the square. This is going to be square root of 29. And for example, let's say I would like to multiply this vector to another vector v with the components 1, 1, and 2, and u multiplied as a v, it's going to be multiplication of the first component, it's going to be 2, plus multiplication of the second component, it's going to be 3, plus the multiplication of the third component, it's going to be 8. So this is 13. So it is very useful, it is very important to know how to find the lengths of the vectors and how to multiply the 2 vectors as a dot product, because it allows us to find the angle between the 2 vectors. So the cosine of the angle between the 2 vectors u and the v, this is going to be equal to the u dot v divided to the length of the u multiplied to the length of the v. Okay, so you see, so the cosine of the angle is equal to the multiplication of the 2 vectors as a dot product, right? And when we consider the perpendicular vectors, the angle between them is going to be equal to pi over t, right? And the cosine of the pi over t is going to be equal to the u dot v divided to the lengths, right? To the multiplication of the lengths. And cosine of pi over t is equal to the 0, which implies that u dot v is equal to the 0 when the t vectors are perpendicular, and vice versa. If the t vectors are perpendicular, their scalar product or their dot product is equal to the 0. So when the t vectors are parallel, when we talk about the position vectors, right, which is starting from the same point, which is starting from the origin, so the t vectors are going to be parallel if they are on top of the other. So if we're given the t vectors u and v, so these t vectors are parallel if it is possible to obtain one of the vectors by scaling the another one, by just changing the size, just the length of the second one, and we can do this by just multiplying the second vector to some constant. So if it is possible to multiply the u vector to some constant k, let's say, and obtain the vector v, in this case the t vectors are called the parallel, and if the scalar multiplication of the t vectors is equal to the 0, then the vectors are perpendicular. So another type of the operation with the vectors is called the cross product. So this is the special operation which is defined when we're interested to know the third vector, which is going to be perpendicular to both of the vectors. So let's say we're given the t vectors u and the v with the components as usual u1, u2, u3, and v1, v2, v3, and we're interested to know what is the vector omega, which is going to be perpendicular to both of the vectors at the same time. And it appears the cross product of these two vectors u and v gives us this vector. So omega, which is perpendicular to both of this vector, it can be obtained by multiplying the u to the v as a cross product. And this can be obtained by finding the determinant of the 3×3 matrix. So on the first row, we need to always write the I, j, k. On the second row, we are going to write down the components of the first vector. And on the third row, we're going to write down the components of the second vector. Then we need to find the determinant. So finding the determinant of the 3×3 matrix is pretty much straightforward. So in order to do this, we need to cross out the first entry of this matrix. It is going to be, then we need to multiply the I, the first entry, to the determinant of the matrix which is left. So this is going to be ut, u3, v2, v3, minus j. We're going to cross out the j now, right? So, and the row and the column where the j is located, and multiply to the determinant of the matrix which is left, right? If you cross out the j, and the matrix which is left is u1, u3, v1, v3. So plus the k, which is the third entry on the first row, and we're going to cross out its column and the row where it is located, and multiply it to the determinant of the matrix which is left, which is going to be u1, u2, v1, v2. Finding the determinant of the t by t matrix is even more easier. This is going to be I multiplied to these two entries, multiplication, minus the multiplication of these two entries. It's going to be u3, v2, minus j component of this vector is going to be u1, v3, minus u3, v1, plus the k multiplied to the u1, v2, minus v1, u2. So we obtain a mega vector with the three components, right? Which is going to be perpendicular to the u and the v at the same time. So let's consider an example. So let's say we're given t vectors. What I would like to do is I would like to multiply these t vectors as a dot product, and at the same time I would like to check what is their cross product. So u dot v is going to be equal to the t 3, 0, 2 multiplied to the 1 minus t and 3. This is going to be equal to the 3 plus 0 multiplied to the minus t plus t multiplied to the 3, which is going to be equal to the 3 plus 6, which is 9. And u cross v is going to be equal to I, j, k, 3, 0, 2, 1 minus t, 3. So I'm going to cross out the I first of all, right? This is going to be equal to the I multiplied to the 0, 2, minus t, 3, minus j. Let me cross out the j. This is going to be 3, 2, 1, 3, plus the k, which is going to, if I cross out the row and a column where the k is located, the matrix which is left is 3, 0, 1 minus 2. So what I need to do is I just need to calculate the determinants of the three 2 by 2 matrices. It's going to be I, which is going to be 0 minus minus 4, which is going to be 4 simply, minus j multiplied to 9 minus 2, plus k multiplied to minus 6 minus 0, right? So this is going to be 4i minus 7j minus 6k, or we can write this down using the 3 tuple, 4 minus 7 minus 6. So this is the dot product of the two vectors, and this is the cross product of these two vectors. At the same time, we can find the angle between these two vectors, the cosine of the angle between these two vectors. This is going to be equal to the dot product, right? So u dot v divided to the multiplication of the lengths. So this is going to be equal to the 9 divided to the length of the u, which is going to be 9 plus 0 plus 4, multiplied to the length of the v, which is going to be 1 plus 4 plus 9. So this is going to be equal to the 9 divided to the square root of 13, multiplied to the square root of 14. Okay, so now let's talk about the lines. So we would like to define the line in the higher dimensions. So we can't just write the line as usual y is equal to the kx plus b anymore. So let's say we're given some point. We are given this point. We know its coordinates. Its coordinates, let's say, is equal to the x0, y0, z0. This might be, for example, 2, 3, 4, right? And we're given another vector which is parallel to this line. So these two things are given, and I would like to find all the points along this line. For example, I would like to know the coordinates of this point. Okay, so what I'm going to do is I would like to create a vector, right? So going from p0 to the p, and the position vector. So and this vector is going to be parallel to the u, right? So the two vectors are parallel when we can obtain the vector p0 p by multiplying the u to some constant t, right? So this vector p0 p can be obtained by subtracting the p from the p0, right? And this is equal to the u multiplied to the t. From here we can find the coordinates of the point x, y, and z by adding the coordinates of the p0, which is going to be x0, y0, z0, plus the coordinates of this u, let's say u1, u2, u3, right? So u1, u2, u3 multiplied to the constant t. So we call sometimes this t as a parameter. So this looks like very much similar to the parametric equation of the line. So actually this is the equation of the line. So by substituting the coordinates of the point on the line which is given, and by substituting here the coordinates of the vector which is parallel to the line, we can find all the points along this line. So let's consider an example. So we're given t points, and I would like to find a line which is passing through these 2 points. So in order to do this, what I need to do is I need to create a vector going from one point to the second, right? And I just need to scale this vector, right? So let's find it. Let's say this is u, our vector which is parallel to the line, and this u is obtained by subtracting the starting point from the ending point. 4, 3, minus 1, minus 2, 1, minus 3. If I subtract this, this is going to be 2, 2, and 2. Okay, so and now in order to construct what I want is I would like to find the coordinate of any point along this line, right? And this x, y, and z is going to be equal to the starting point or any point. So in this case, this is 2, 1, minus 3, plus this vector u, which is 2, 2, and 2, multiplied to some parameter t, right? If I multiply the t to this vector and add this to this vector, this is going to be 2 plus 2t, 1 plus 2t, and minus 3 plus 2t. So basically, at the same time, we can derive the parametric equation of the line as x is equal to the t plus 2t, right? X coordinate is equal to the x coordinate on the right and left. Y is equal to the 1 plus 2t, and z is equal to the minus 3 plus 2t. So this is called the parametric equation of the line where the t is a parameter. So by changing the values of the t, by giving different values for the t, we can obtain the different points along this line. So now let's define the planes. So in order to do this, so let's say we're given a normal vector to the plane, which means that this is the vector with the components usually is given with A, B, and C. This is going to be perpendicular to every single vector on the plane, right? So if you create any vector on this plane, this vector n is going to be perpendicular to all of them at the same time. And at the same time, we're given a point on this plane. So what we want is I would like to find the coordinates of every single point on this plane. So let's say I would like to find the coordinates of this point with the coordinates x, y, and z, right? So in order to create this, I know the concept right here. So I know that if I do the vector like this, going from p0 to the p, this vector is going to be perpendicular to the n, right? And I can create this vector by subtracting the starting point from the ending point. So basically x, y, z minus x0, y0, z0 is going to be perpendicular, right, to the n. What does it mean? It means that if I multiply this vector to the normal vector as a scalar product, as a dot product, this is going to be equal to the 0 because they are perpendicular, right? So now, using the properties of the dot product, I can open up the brackets. It is going to be equal to the x, y, z multiplied as a dot product to the n. So let me write down the n using its components a, b, and c, which is minus x0, y0, z0, the coordinates of the point on the plane, multiplied as a dot product to the components of this normal vector is equal to the 0. And actually I can write this down as equal here, right? So let me multiply this 2. It is going to be ax plus by plus cz is equal to the multiplication of this 2. It is going to be ax0 plus by0 plus cz0. So sometimes you might see that this constant, right? This is the constant because the a, b, c, 3 numbers are given, x0, y0, z0 are given, right? This is, so sometimes we denote this as a t in order to write down the equation of the plane in the form ax plus by plus cz is equal to the d. So let's consider an example. So what we want is we would like to find the equation of the plane which is passing through this point and which is going to be perpendicular to this plane. Okay, so the equation of the plane is given like this. Let me write this in a normal form, right? So I would like to write this as a 5x minus y plus, minus z is equal to the 6, which is the way of how we write down the equation of the plane. So where you see, so the coefficient before x, y, and z form actually the normal vector, right? So we are given this plane, the blue plane, and we know the components of its normal vector. Let me denote this as n1. This is going to have the components 5, minus 1, minus 1. And I would like to create this purple plane which is going to be perpendicular to this, right? So in order to do, the only thing which I know is I know the coordinates of the point on this plane was a 2, 0, and 1, and also I know that this is perpendicular to this one, but I need to know the normal vector to this, right? So let me denote the components of the normal vector as the x, y, and z, right? And since these two planes are perpendicular, the normal vectors should be perpendicular as well. So what we need to do is we need to multiply the 5 minus 1 to the components of, so let me denote this as a, b, c as usual, a, b, c, and this should be equal to the 0. So let me multiply this. This is going to be 5a minus b minus c. This is going to be equal to the 0. So I got 3 unknowns in one equation. It means that I can choose any value for the a, for example 1, any value for the b, for example 1. And if I substitute this to here, it's going to be 5 minus b, or minus 1, sorry, because I substituted b to be equal to the 1. And minus c is equal to the 0. From here, I can find that the c is equal to the 4, right? So the normal vector, the components of the normal vector, for example, might be 1, 1, and 4, right? In this case, this normal vector is going to be perpendicular to this vector n1. So this is how we kind of choose this normal vector n. So now, if we're given the normal vector and a point, we can create the equation of the plane easily, right? So we need to multiply the components of the normal vector to the x, y, z. This is going to be 1, 1, 4 is multiplied as a dot product to the x, y, and z. And on the right hand side, I need to multiply the components of the point, which is 2, 0, 1, to the normal vector, to the components of the normal vector, which is 1, 1, and 4. If I multiply this on the left, we're going to have x, y, plus 4z. And on the right, we're going to have t plus 4, which is basically 6, right? So this is going to be the equation of the plane, which is perpendicular to the given plane. So sometimes it is interesting for us to know the distance between the point and the plane as well. So let's say we're given a plane with the equation ax plus by plus cz is equal to the d, right? From here, we can easily trace the components of the normal to this plane, right? This is going to be a, b, and c, the coefficients before x, y, and z. And now we're given another point outside the plane with the components x0, y0, z0, and I need to find the distance between this point and the plane. And this distance is actually the shortest distance to the plane, which is going to be perpendicular to this plane, right? So let's do this in an example. So let's say we're given a plane with this equation. It means that the normal of this plane has the components 3, 2, and 6, right? And we're given another point which is outside the plane, and I need to find the distance between the point and the plane. So in order to do this, what I'm going to do is I would like to choose any point on this plane. So let's choose any point, for example, this point. And what does it mean? It means that I need to find the pairs 3 numbers, x, y, and z, which is going to satisfy this equation. So when I'm given one equation and 3 unknowns, I can choose 2 of them as I wish. I can choose anything for them. So for example, let's choose x to be equal to the x to be equal to the 0, sorry, y to be equal to 1. Then if I substitute this, this is going to be 3 multiplied to the 0 plus 2 multiplied to the 1 plus 6 multiplied to the z is equal to the 5. From here I can find that z is equal to 6z is equal to the 3. From here z is equal to 1 over 2, right? So the point with the component 0, 1, and 1 over 2 is lying actually on the plane because it satisfies this equation, its equation. So or let me choose another point. So to work easier, so let me choose z to be equal to the 0, x is equal to the minus 1. Then if I substitute this, this is going to be 3 multiplied to the minus 1 plus ty plus 6 multiplied to the z is equal to the 5. So this minus 3 goes to there. It's going to be ty is equal to the 8, y is equal to the 4. Right? So this point is lying on the plane because it satisfied this equation. So actually you can choose any point on the plane, right? So this is going to be minus 1, 4, and 0. So now I would like to make a vector from this point to this point. Okay, so let's denote this vector as a u, and I can easily find this vector by subtracting the starting point from the ending point. And I need to find this distance, right? Distance. So if I multiply the length of this vector u to the cosine of the angle between this line, right, and this vector, this is going to give me exactly the length of this line, right? If I multiply the length of the u to the cosine of the angle between this line and this vector, this is going to give me the distance between the point and the plane. So actually the cosine of the alpha, so the angle between this line and this vector, is the same as the angle between this vector and the normal vector of the plane, right? Because you can put this normal vector to any place. If you would put this normal vector to here, this would be the same angle here, right? So we know how to find the angles between the two vectors. This is going to be u multiplied to the n as a dot product divided to the norm of the u multiplied to the norm of the n. This is going to be equal to, I can cancel out these two numbers because when you find a norm or the length of the vector, this is going to be a number, not a vector anymore. So this is be u multiplied to the n divided to the norm of the n. So now let us find u first of all. So u is going to be when we subtract the starting point from the ending point. Minus 1, 4, and 0. This is going to be 2. Minus 2 minus 4 is minus 6. 4 minus 0 is 4, right? And our normal vector is given with the components 3, 2, and 6. 3, 2, and 6. So we just need to substitute everything there to this formula. So u dot n divided to the norm of the n. This is going to be equal to 2. So please note that I need to take its absolute value, obviously. Minus 6, 4 dot to the 3, 2, and 6 divided to the length of the normal vector, which is going to be 9 plus 4 plus 36 is equal. So 2 multiplied to the 3 is 6, minus 6 multiplied to the 2 is minus 12, and 4 multiplied to the 6 is plus 24, divided to the 4 multiplied to the 36 is 40, plus 9 is 49, square root of 49 is 7. So I need to take its module. This is going to be equal to the minus 6 plus 24 is 18 over 7 is the distance between this point and the plane.